Hello everyone, my name is Leila Tanraldo. Today I will be explaining the experiment I performed my Physics 102 course, where I investigate the Hall effect and how Hall voltage depends on both electric current and magnetic field.
The Hall effect describes how charged particles inside a conductor experience a sideways force when both electric current and a magnetic field are present. This force creates a voltage difference across the conductor, called the Hall voltage. In my experiment, I studied this voltage under two separate conditions. In part 1, I changed the current while keeping the magnetic field constant. In part 2, I kept the current constant and changed the magnetic field by adjusting the distance between the magnet poles. This experiment was carried out using a Hall sensor, a gasometer, a DC power supply, a digital multimeter, and a Hall measurement device. And this is my experimental setup. The Hall voltage is given by the equation VH equal B times I times RH, where B is the magnetic field, I is the current, RH is the Hall coefficient. According to this equation, if B is constant, VH should increase linearly with I, and if I is constant, VH should increase linearly with B. First, I measured the magnetic field using the gasometer. At a 1.5 cm distance between the magnet poles, in part 1, I kept the magnetic field constant at 1.480 kg and decreased the current step by step. The Hall voltage decreased linearly from 190 mV at 0.47 mA to 39.6 mV at 0.16 mA. And I used to my calculation filled the graph 1 and table 1 in about part 1. In part 2, I kept the current constant at 0.4 mA and changed the magnet gap to vary the magnetic field 1 cm, 1.5 cm, 2 cm, 2.5 cm, and finally 3 cm respectively. The measured B values range from 0.740 to 1.734 kg, and the Hall voltage changed accordingly from 87.3 mV up to 107.8 mV. Again, the graph showed an almost linear trend, verifying VH and B. Small deviations occurred because of practical limitations like sensor sensitivity, environmental magnetic noise, and slight misalignment of device. And I used the calculations about my part 2, filled the graph 2 and table 2. From the second measurement in table 2 at 1.5 cm, the measured Hall voltage was 100.4 mV. Using the formula and assuming a Hall coefficient of 51 kΩ, the theoretical magnetic field was calculated to be 0.0492 kg. But the gasometer measurement at 1.5 cm was 1.502 kg, leading to percentage error of 96.7. This large error comes from the fact that real magnetic fields are difficult to measure perfectly, and small alignment mistakes cause large difference. The high sensitivity of the Hall probe and variations in temperature and current also contribute to this error. In conclusion, this experiment successfully demonstrated the Hall effect and confirmed the theoretical behaviors of Hall voltage. Both graphs clearly showed the Hall voltage increase proportionally with current and magnetic field strength. Although the percentage error in the theoretical magnetic field calculation was high, the difference in the data matched the expected physical behavior. This experiment shows how the Hall effect can be used to measure magnetic fields and study the motion of charge carriers inside the conductor.